Yeah, so just one thing that I forgot to say on the previous notebook, actually, that I was reminded of. Oh, did it? Yeah, right.
Yeah, from the other.
With the other mouse, yeah. So yeah, one thing that I forgot to mention on the previous notebook, actually, that came out of some of the people I was just chatting to. This dumb strategy that I did with just canonical simulations at a series of temperatures, but there is a way that I could piece those together into a distribution that goes across the entire energy range, which is I could use a multi-state Bennett acceptance ratio, which I think I've learned is called something else in its community, where I just take the samples that I generated at a temperature, and I would pick one of them at random, and I would propose moving it to another temperature, i.e. changing beta. What would be the ratio of these two probabilities, average that over many samples, and then that would give me a factor that I could multiply each histogram by to piece them all together and make one big histogram. So I could do that. It wouldn't solve this problem because in the process of generating the samples at low temperature, I've not had access to the high energy states. I need to move between these low energy traps. And I'd still be wasting a lot of time generating samples in the same region of energy space in parallel. So that's not something we tend to do, but if you've already got the data, why not? Okay, so back to the multi-canonical sampling. So that did 5 iterations. I could run it for longer if I wanted to. I've got a slightly wobbly set of this bias function, a set of estimate of this bias function. And I've got sampling across the entire energy range. Again, picking up on some of the questions, I'm only ever using the samples that I've generated at the last cycle, i.e. with the most recent bias weights to construct the next biased weights. You could conceivably think about storing each set of weights that you generate and working out how do you need to reweight the samples that you've made from one bias weight to the next so that you're using all of those samples rather than throwing them away. I will talk about a method towards the end which throws nothing away, that uses all of the samples. The other thing that maybe I should have mentioned, I've made a slightly arbitrary choice here that I'm going to do 5 cycles. I'm too far up. Where am I? I should be here. 1,000 frames per cycle. I'm not claiming in any way that's optimal. Maybe I should have shorter cycles. I should update the bias more often. The risk of doing that is that if I've not visited all of my bins, then I'm going to think I need to bias heavily towards that bin that I've not visited. And I might introduce a spike in my bias weights that then takes me many iterations to heal. So it is advisable to try and sample all of your bins, or at least all of the ones within the currently accessible energy range, the range you've currently been pushed out into, before you update the weights. But I'm not in any way claiming that is the optimal update rate for the weights. That's the kind of thing that people play with and optimize and publish papers about fancy adaptive ways of figuring out how often you should refresh those weights and so on.
The number of bins is,
also, the number of bins, is something that I've chosen. If I make those bins very narrow, I'm more likely to hit this problem where I've got a gap in my energy distribution that's going to cause me a problem that will take a while to heal. I want reasonably high resolution because I'm looking for a high precision estimate of where the peak in the heat capacity is. And on that context, I should have mentioned as well that some people don't use discretized energy bins. Some people do kernel density estimates and get smooth functions out, if that's the thing that you want to do. I tend to default to doing discretized bins because quite often I'm not doing this in energy. I'm doing this in number of particles in the system, and the hyperparameter is a chemical potential, and the number of particles is naturally discrete. So you would always deal with that using a histogram type approach. Yeah.
Sorry, so why does the bin resolution have to do with the resolution of you finding the heat capacity? I mean, I would think the x-axis for the heat capacity is temperature rather than.
It is, yes, but if I'm I guess we'll see a bit later on, but when I'm doing histogram reweighting, I'm taking the energy of all samples in the bin to be the energy in the middle of the bin. So I'm losing some energy resolution, and that will cost me a little bit in the accuracy of my heat capacity. Yeah, yeah. I don't have to do that, and I'll show different ways of doing that. Okay, so as a histogram, a final histogram with a fixed set of weights. Actually, I'm not calling this a final histogram. It's the histogram from the last cycle of the bias refinement procedure. I've got my bias, and I've got some broad histogram that covers the entire energy range. So what can I then do with that? Well, because I want good statistics with a constant set of weights so that I can reweight my samples to get histograms at any temperature, what I'm going to do now is take my final weights and run a simulation with just fixed weights for longer than that one cycle. So this would be the next step. I could try and do some more sophisticated things that miss this step out, and we will in the next notebook. So now I'm not changing the weights. I'm just generating a whole bunch of samples with fixed weights. I probably should have set that running while we were on a break. That's going to take quite a long time. All right, so what I'm going to do is I'm going to cheat. I'm going to stop that. And thankfully, I've anticipated this problem. And I'm just going to load some samples that I made earlier that are coming from a file. Oh, no, sorry, that's not what I'm doing. No, I do need to run that. Apologies. So that's not what I'm loading from a file. So the next thing that I want to do is I want to take the estimate, the unbiased estimate of the energy histogram at the temperature where I'm running the biased simulation, and compare it to just a standard canonical simulation at that same temperature, and make sure I'm getting the right statistics. So just a sanity check that I can reweight. Anyone know any good jokes? Well, maybe I can talk through the next part while that's running. So what I'm going to do is take the samples of energy that I'm generating with that fixed set of weights. I'm going to use my unbiased histogram routine to say, okay, go through each one of those samples, give it the weight that it would have had in a simulation with a bias of V equals 0 at this same temperature, and just plot that histogram. I'll come back to that. And then the next more interesting step is, given that set of samples, how can I get histograms at other temperatures? So that's, you know, I think you all know what's coming here. Having generated that set of samples with fixed weights at one particular temperature that I'll call beta 1, if I want to know what weight should that have at some other temperature in the absence of any bias, then I just multiply it by the Boltzmann factor that I want at that new temperature, and I divide by the Boltzmann factor. So there's a minus sign there, but that I'm not dividing, I'm multiplying. I've got rid of the minus sign. The Boltzmann weight of the biased simulation at the original temperature. So if what I care about is just the energy, what is the probability of sampling a particular energy, then that gets me everything that I need, because I can then rebuild the energy histogram at any temperature that I care about. But I might care about sampling things other than the energy. So during this simulation that is still running up here, I am not just building up energy samples, I'm also building up samples of the end-to-end distance. I don't know how samples of the end-to-end distance depend on I don't have an explicit formula for how end-to-end distance depends on temperature. But what I do know is for every sample of the end-to-end distance that I've measured, or that I've taken, what was the energy at the time? So I've got pairs of samples for the energy of a microstate, the end-to-end distance of the microstate, And if I know the energy of that state, I know how to reweight it to the unbiased ensemble at the other temperature. So provided I've got a run where I know what the bias is, and I'm sampling the thing that I care about along with the corresponding energy, I can reweight any function of that microstate that I care about to some other temperature. So that's what we'll do when that simulation finishes. I'm sure this was running faster yesterday, but we're nearly there. The other advantage of making you wait while this happens, by the way, is the last method. There won't be much waiting, and we'll get better results. So,
how close is this to the first multi-column?
As if you were to dig out that paper from 1992, I think I'm probably 90% similar to what they do in that paper, and then yeah, people have built on that and done fancier ways of refining the weights and so on. I've not mentioned adaptive umbrella sampling yet, and what I'm doing here, this procedure of coming up with a guess of the weights that I need to get a flat distribution, and then running on those weights and iterating, is sometimes known as adaptive umbrella sampling. In that context, you normally divide up the range of the thing you're sampling, in this case the energy, and you do sampling within windows and build weights adaptively in that area. And adaptive umbrella sampling was again sort of mid-90s, and then it was reinvented and called metadynamics in the 2000s with slightly different bells and whistles. That's a controversial statement that some people would shoot me for. Okay, so here I'm building the histogram that's come from the multi-canonical sampling. I've reweighted all the samples to get the orange histogram, and then I've loaded from file a histogram from a canonical simulation at a single temperature that was 10 times longer, and yeah, we've got the same histogram. If I was doing all this at the lower temperature, I wouldn't be getting the same histogram, because we've established that the histogram at low temperature from the single temperature simulation was wrong. It had errors in it. But at the high temperature, it's basically the same. There's no problem there. At the high temperature, there's no traps. Okay, so I'll now do the histogram reweighting procedure. So because I know that all samples in an energy bin to within the resolution of my discretization have the same energy, if I want to reweight that histogram, I just multiply the height of the bin by that reweighting factor that takes into account the difference in temperature and the removal of the bias. And then if I have the histogram, I can compute the variance. The variance gives me the heat capacity. And because I can now do this at any temperature that I choose to care about, as long as those temperatures only need to know about energies over the energy range I'm sampling, I can have I can look at whatever temperature I want, really. So I can look at a much finer resolution of temperatures than I did when I was running a separate simulation for each temperature. I won't plot all the histograms, because then my axes will just be crowded with color and you won't see anything. But I'll plot all the heat capacities, and I'll plot all of the mean energies. So the mean energies is just a dot product of the energy in the middle of the bin with the new probability, the weight for that bin at the new temperature and without the bias. And to get the get the heat capacity, I'm just working out in each bin what is the mean squared deviation of that energy from the mean, and I'm working out the variance that way. So we get back a much better version of the plot that we had in the previous notebook. I'm now much happier with my low temperature histogram, my T equals 0.1, because I'm using information from multiple visits to this coiled state where it coils in different ways, because it's had access to high energy routes to get back into different coiled states. I can sample with a much finer resolution in temperature. Essentially, I can be continuous in temperature, and my spurious massive heat capacity at low temperature is gone. And I've got this peak in the heat capacity that's a signature of a transition from the coil to the globule as I increase the temperature. if the chain were to get longer and longer and longer, that peak would get sharper and sharper and sharper until eventually it was a delta function indicating that there'd be a discontinuity in the energy here as I went through a first order phase transition.
Sorry, that's what you'd expect if you send n to infinity?
If I went n to infinity, I'd see a discontinuity in the energy, and I'd see a delta peak in the heat capacity.
Can that actually be an issue with the fact that the states in the same bin don't have the same energy?
So yeah, it might be. I'm about to test that. So you'll see that how much of an issue that is. Okay, so that's much better. And as I mentioned, I don't just have to reweight the energy because I've built up this list of pairs. I know the energy, I know the end-to-end distance, so I can compute the probability of each end-to-end distance sample and build up statistics on that. I won't bother going through the details. So there you go. There's the average, the mean, or the expectation of the end-to-end distance of the polymer as a function of temperature. And you can see as it transitions from the coil to the globule, there's a change in slope. Okay, so to answer the question that was just asked, this first set of data, all I've done there is I've taken the energy of all states in the bin as being the same, as being the mid-bin energy. I've used that energy to compute the weight to the factor that I need to rescale that bar of the histogram. I could take all the individual samples of energy. I know what bias weight they had because the bias weight is the same for every energy within a bin. So I'm getting rid of that approximation by reweighting the individual samples of energy that I've taken rather than reweighting the bar in the histogram. And then we can compare the two. So now I'm looping over samples. I'm computing a weight for every sample rather than a weight for every bar in the histogram, which is what I did for the end-to-end distance. I'm just now doing it with the energy. That's just running the same thing. So for all the temperatures, loop over the samples, compute the weight with which I should now count each sample for the new temperature without the bias. Michael?
Am I right to understand that the bin size you chose, that governs how fine a resolution you can have?
No, I can have essentially infinite resolution on my temperature scale. But my estimate of the mean energy from the histogram is going to be affected by the fact that I've discretized the energy, as will my estimate of the heat capacity, because I'm saying there's only 50 possible energies. So I'm going to have some small error there, yeah. But if I reweight the energy samples, rather than just multiplying the bar of the histogram, I'll get something that doesn't have that limitation, which is, yeah, exactly what I'm about to do. So now I'm reweighting the samples rather than just the height of the bar. And, there's not, I don't care about that difference. That's the same curve as far as I'm concerned.
Why is it worse for lower temperatures?
Why is it worse for lower temperatures? Oh, I hadn't actually spotted that. I hadn't spotted that it was worse for low temperatures. Can I understand? So which one is the histogram we went in? I don't know. I think that's through.
I guess it's the most extreme reweighting, probably.
Yes, but then I had lots of samples in my lowest temperature bin. If I had to guess, I'd say it's because the energy range that I've defined as going from -6.1 to +4. I did one simulation at t equals 0.1 to decide where to put the minimum energy. And I might not have done the simulation that had the minimum energy coil. So I might actually be missing some of the energies that are important at very low temperature. So that's probably on me. I've been lazy in defining my minimum energy. I should have perhaps gone a bit lower.
Maybe it has to do with the bin width being sort of relatively large versus how wide the distribution is.
Yeah, that could be it as well. Yeah, yeah.
Very narrower than the size of the bin. Yes, anyway.
So one thing I just wanted to, before moving on to the next thing, I wanted to say something about parallelization, because there's a perfectly fair comment here that when you did this the dumb way, okay, it was less efficient, but you might have got your answer faster. And maybe that's what I care about, because I've thrown more processors at it. I've done one simulation per processor, and maybe that gives me a higher speed answer. If I was going to make use of parallel computing to do this, I wouldn't do one temperature per processor. What I would do is I would divide up my energy range into windows, okay, that would overlap slightly by 1 or 2 bins. And then each processor would simulate within a window. So it would build up the multi-canonical weight function within some subset of the energy range, okay? And then I would, either using M-bar, band acceptance ratio, or more often than not, just piecing together the weights at the boundaries, looking for a smooth and continuous function, I'd reconstruct the bias function over the entire energy range after breaking it up into windows. So slightly controversial statement, and I've never been able to demonstrate this myself. Some people will tell you that gives you a super linear parallel speedup. But if you throw P processors at it, you will gain more than a factor of P in converging your answer in a given amount of CPU time. And the reason for that is quite often your convergence of the weights, the limiting factor is how long it takes the Markov chain to go up and down the energy range. Okay, so you need your total run length from which you build the histogram to be very many times longer than the time it takes your sampler to go up and down the entire energy range. Otherwise, you're going to end up with a biased sample because you just want to be up and down twice, and I kill the simulation when I'm at one end. I'm going to be slightly biased towards that one end. Whereas if I break up into smaller windows, it now takes less time for the sampler to go backwards and forwards across the energy range. So I converge faster, and so overall I get a super linear speedup. I gain more than a factor of P in my speed of convergence to a solution. And that, I think, someone's going to ask me, is there a paper about this? There are bits of papers about this. There's people have done studies on very expensive systems to simulate, and then there's a paragraph somewhere where they say, oh, by the way, it's much more efficient to parallelize in this way, break up the energy range. Because the other obvious way to parallelize would be to just have multiple samplers, multiple walkers, Markov chains that are all adding into the same histogram, contributing to the same weights. And that also turns out to be less efficient than breaking up the energy range.
So, this is a super linear speedup. Would it make sense even with one processor to break up your range in this way and run multiple small windows?
Yeah, I guess it would. Yeah.
Does that break down at some point? Or
I've never tried it, but yeah, it's a logical thing to try. I mean, I guess once you get to one bin, then yeah. Yep. So that is a limitation of all these methods, is I have to know what energy range I care about in advance, but I can get that easily enough by just running a cheap little simulation at the lowest temperature I care about and the highest temperature I care about, and then looking at the minimum of that and the maximum of that, and that gives me the range. But actually, from the question we had about why did I have this difference at low temperature, I probably messed that up in this case. Yeah. Okay, so that's kind of the basic multi-canonical sampling procedure. Again, many variations on the theme. And lots of groups have their own recipe for doing this kind of thing. Are there any questions on that before I move on?
Can I ask you how does the methodology scale with the dimension? I mean, if you start
that's quite. So as a physicist, I care about d equals 3. And oh, okay, right. So you mean, so okay, so how to scale the length of the chain, basically, with the number of beads? Yeah, okay, right. I can't give you a formal expression for that. It works for large N. We use it for large N. What I will say, though, is in this particular system, as N gets larger, there are other sampling pathologies that come in, and you then have to get into clever moves. You have to get into doing the...
Okay, so the problem is not really on...
The problem is not this. The problem is
but more on the
yeah. So these single particle moves are probably not going to get you good statistics once you get to a longer chain that can ravel itself in. Yeah. Yeah. So then would be people might have heard of Rosenbluth sampling, which is a form of configurational bias Monte Carlo. So if you have a long chain, that there are moves where you say, okay, I'm going to delete half the chain and I'm going to regrow it. And then you make a number of trial segment regrowth moves as you move along the chain, regrowing it, picking the one that gives you a low energy segment. And then you adjust your acceptance ratio to compensate for that to maintain detailed balance. I mean, if people are interested, I do actually have a notebook on that, that shows that the correlation, the autocorrelation time along the chain, if you make those moves, is massively, massively shorter than if you make single particle moves. So those moves are quite expensive, but they save you a huge amount of samples because they decorrelate much faster.
Are there any kind of like small strategies to keep the edges of the...
You mean other than just run a high temperature and a low temperature simulation? Not really, no. I mean, if it's a model that you already know quite a bit about, so that if I know the ground state energy of this system of particles is a close packed crystal, then I've got gradients, I've got forces, so I could do an optimization problem. I could find the absolute minimum energy if I knew what the structure of it was, and then I could, I guess if I'm not normally interested in gases, but if I was interested in going all the way up to energies where the gas phase is relevant, then in this kind of model, I know the maximum energy is 0 because there's no interactions, right? So if I know something about the model, I can do something smarter. But the something smarter will be what Livia tells you this afternoon. Yeah. Not that I'm aware of, but it's a thing that could be done. Yeah. I mean, the project that Livia and I have is using. We don't have energy, we have volume, but we've done some nested sampling, and then we found things we're interested in, and then we've run other more conventional Metropolis Monte Carlo methods to poke at details. Yeah. But yeah, I don't want to spoil this afternoon. So. Is there any
diagnosis to say like, well, we're good?
And since I've picked a good energy range,
yeah.
Well, I guess if I plot histograms at temperatures I care about and they're truncated, that's telling me I've missed some of the energy range that I care about.
So it's only something like at the very end.
Yeah, exactly. Yeah.
So ideally, you would like this histogram to be a flat.
In a perfect world, yeah, but it doesn't have to be. It just has to be good enough that I've got good statistics everywhere. Yeah. Okay. All right, how am I doing for time? All right, I've only got an hour to go through two other methods, but the actual core differences of these other methods are not massive. So this is, until recently, Wang-Landau sampling was the thing that we did. If we wanted to explore a model in my group, is we just defaulted to Wang-Landau sampling. So very, very similar kind of concept to multi-canonical sampling. As I mentioned earlier, there's two parts to Wang-Landau sampling, and quite often people just focus on the second part and say, I've done Wang-Landau sampling, and they forget about the first part. And David Landau gets very upset. So I'm going to make sure that I stress that there are two parts to this. So the first part of this is the realization that if what I want is to sample each energy macro state with equal probability, then I should do a Markov chain walk where the probability of having a particular energy is 1 over the density of states in energy. So if I've got some large number of states that can be sampled in one particular bin, some small number of states that can be sampled in some other particular bin, and I sample in inverse proportion to the number of energy states in each bin, then I'll get uniform sampling across the energy range. And that G of E is the density of states in energy. It's the number of states that exist between E and E plus DE which I've discretized to be within the energy range of a particular bin. Okay, so you can think of this as I'm doing a standard Metropolis Monte Carlo at infinite temperature. So the e to the minus beta u just turns into 1. And then my unbiased probability will just be the density of states. And so if I want to have a flat probability, I sample in inverse proportion to that. So now for deriving my Monte Carlo acceptance rule, my weight, I'm replacing the Boltzmann weight with 1 over the density of states. And if I do that and I derive the probability of accepting a move, it'll be this. So if I'm going from state A, microstate A to microstate B, then it's the minimum of 1 or the ratio of the density of states at those two energies. Because the problem is I don't know the density of states. If I knew the density of states, I have all the information I need to write down the probability distribution at any temperature, because that's just density of states times Boltzmann factor. So it's another, I'm going to have to bootstrap this again. I don't know G of E. So that's the first part of the Wang-Landau procedure, is I'm going to do a sampling where rather than using a Boltzmann probability for each microstate, I'm using 1 over the density of states in energy as the probability of each microstate, and that will get me flat sampling. The second part of Wang-Landau, which is the part that most people pick up and run with, so even if what I'm not trying to compute a sample distribution of, if that's not the energy, if it's something else, if it's some collective variable of the type that we heard about yesterday, then some people use this iterative Wang-Landau procedure just to get the weights they need to get uniform sampling with any collective variable. But strictly speaking, Wang-Landau sampling is this thing with the Boltzmann factor replaced with 1 over the density of states, and then using this recursion procedure. So the procedure to bootstrap and estimate the density of states, this is the way that Wang and Landau did it. People again have modified this and tweaked it and refined it and come up with their own adjustments. So we define something called F, which is called the modification factor, and we set that equal to Euler's constant, some number that's a bit bigger than 1. We set the density of states for all of my energy bins to be 1. Okay, that's a terrible estimate. I then run a Monte Carlo simulation using this as my acceptance criterion, using that ratio of density of states. And every time I visit a microstate, I look for which bin I've landed in, and I multiply my estimate of the density of states in that bin by F. Okay, so I'm saying I visited this bin. I now know there's more states in this bin. So I'm incrementing my estimate of the density of states. As you're doing that, you're updating your estimate of G. You're also recording a histogram of how often have I visited each energy bin, just counting with weight 1 in each bin that you visit. You do that until your histogram is roughly flat. And then you say, OK, I've built up an estimate of the density of states that's giving me a roughly uniform sampling, which means I've got the right density of states. I'm going to reset the histogram. I'm going to make F smaller somehow. So Wang and Landau took F to be the square root of F, reducing it. And then you go again. So you don't throw away your current estimate of the density of states, but you throw away the histogram. And now you're refining your estimate of the density of states with a smaller modification factor. And as F gets smaller and smaller and smaller, as you go around that loop many times, you eventually end up with a density of states that's static and stops changing. Okay, so yeah, Wang and Landau, they said F is equal to E initially. I mean, these days I would never start with anything bigger than 1.005, because if you start with a very large F, you're making big changes to the density of states, which if you undersample anywhere due to transient effects or whatever, then you're going to create a big error in the density of states that'll take a long time to heal. So it turns out it's better to make small changes and have the initial iterations take longer to converge than the other way around. What does flat mean as well is Wang and Landau said, well, my histogram is flat. I'm going to update F when all of my bins are within 80% of the mean bin. And again, people these days would consider that to be a bit gung-ho, and 95 or even 99% go to a very flat histogram before you update. So all this you've seen before. This is my function that does the sampling. Oh, I've left some things in here that shouldn't be in here. No, that's fine. Yeah, that's right. So which bin do I need to be in? That's the same as the multi-canonical sampling. I need to keep track of my energy, total energy, so I know which bin to put myself in. I increment the histogram every time I visit a state and accept the move. If I reject the move, I just count that as another visit in the bin that I started in. I'm not multiplying density of states by f. I'm adding log f to the log of the density of states. Otherwise, I'll end up with overflow errors on the computer because the density of states can be a very big number. So we always work with the logarithm of it instead. But that's it, really. Again, it's 3 lines of code, different from a standard Metropolis MC sampler. Yep.
Given the acceptance possibility, you then have assurances as to the fact that there won't be any bins that will be neglected, so you'll always adjust the
So quite similar to the multi-canonical sampling. When I start this thing off, you'll see that initially I'm only sampling the high energy bins. But as I refine my estimate of the density of states to be large in that region, that acceptance probability will push me away from those states, and I'll eventually sample the whole range. Yeah. There's no guarantee that. Now, this is something that is a sufficiently popular method that I think there is actually a more mathematical literature on its convergence properties, and I think it does converge. But whether that's conditional or unconditional, or I've certainly had situations where it has converged very slowly because of exactly this problem. That once I get pushed to the low energy, I've got to go back to the high energy to unravel and go back and sample different states. So it's not immune to that problem on short time scales, but on long time scales, it goes up and down the energy range and is fine. But in a more expensive problem, you really do want to minimize the number of trips you make up and down the energy scale. Okay, so let's define that. Okay, so here's another. One thing to point out here is I'm now not defining a temperature. Right? I'm an infinite temperature. I'm not doing the sampling at any particular temperature that, other than infinity, but I'm still going to get information that's relevant about all temperatures in the range. So if I set that going, what you can see here is I'm just running until f has become sufficiently small. I'd normally go much smaller than that, right? But just for the purposes of this demonstration, I'm making f very small, running a whole bunch of my sampler, computing the flatness. Okay, if I'm 80% flat, I'm using one Landau's number, update f, reset the histogram, go around again, print out the message. So we've already missed an iteration there, sorry about that. So this is my current estimate of the density of states. This is my current value of log f. And you can see already we're getting something pretty flat sampling. In fact, flatter than we were getting out of the multi-canonical sampling at the end of the procedure. So this is working quite well in this case. When that histogram becomes 80% flat, that number f will reduce again. What we missed here is a little bit of a trick, but because we always start at the high end and get pushed, because the density of states is much higher at the high end, and get pushed towards the low energy part of the plot, we always end up with a sort of bias built in that takes a while to heal. So a trick in the code that I just showed is when accumulating the histogram, wait until you've been everywhere at least 10 times, and then kill the histogram without updating f and start again. So at least you've got a sort of semi-equilibrated chain that's going roughly everywhere to avoid that. I mean, you don't have to do that. It just makes the first step converge a bit faster. So the f has now been reduced. I'm now making smaller modifications to this density of states. So how are we doing? We've done two 2 iterations of the Wang-Landau procedure. We've reduced F twice. We're getting a good number of samples in every bin. So the next step is, given that density of states, what can I do with it to compute the things that I care about? And this is where there's already a bit of an advantage over the multi-canonical sampling method. In the multi-canonical sampling method, even if the thing I cared about was the energy, I still did a simulation with fixed weights after I'd refined the weights in order to get the samples I need at a known bias to reweight them to some other temperature. If all I care about is the probability of visiting a particular energy, all I need is the density of states. I don't need any samples of energies. Okay, I've got the density of states. I've got everything I need enough to do that. So I can get my plots that I care about. I don't know how long this is going to take, but I'll leave it running while I talk about the next step. So now I've got a refined estimate of the density of states. This is my energy histogram, right? I know it's the density of states and energy. It's the number of states in each bin times the Boltzmann factor for that bin. So as long as I'm happy with having a finite resolution representation of my energy range, then I'm done. Okay, I can just build my energy histograms. I can compute my mean energy, and I can compute the variance in the energy because I know the probability of having any energy. Has that finished? Or is it going to do one more iteration? So that stopped when I got below 10 to the minus 4. So that's going to do 2 more iterations, isn't it? Do we want to pause for another break while that runs? Is now a good time to do that? Yeah. So maybe reconvene at past, and then I'll finish this one and I'll show you then the final method very quickly.
No.
Just to be awkward, it's finished. I'm mostly interested in how you get to a crystal.
But not gases. So you do know, in your problems, it's frequent to know locations of modes and stuff.
Yes, yeah. I mean, there is a whole other field of people who their entire field is crystal structure prediction. Yeah.
No, because with Garrett, we're working on parallel annealing method that basically is built up on the idea that if you know the location of the node, you can be very efficient in sampling. It might be very interesting to see